A polynomial is any equation that has this form. And while this form looks quite complicated, it's trying to convey something simple. So it's anything that has x's to integer powers, perhaps they're multiplied by numbers, which I'm calling like a sub 2 or a sub 1, and you simply add all of those things together. And this dot, dot, dot just means it can be quite lengthy. There can be many, many terms. Second thing is, in this equation, nothing is factored. There are no parentheses anywhere, so I'm going to call that expanded form to mean that this whole thing is multiplied out. And when this happens, we're going to call the degree of a polynomial this largest exponent n. In example 1, we have these 8 equations, and I want to determine which of them are polynomials. Let's start with this one here. So this turns out that it is, in fact, a polynomial. And the reason is we have x's to integer powers. Some of them are multiplied by numbers. Here we have a plus 1 at the very end, and they're all added together. And in this case, the degree of the polynomial is 3. And that's because it's completely expanded out, so this number is the degree. Looking at this next one, even though this is just one term, this is also a polynomial. So in this definition up here, this just tells you like it can be large, but it could also just be one thing itself. So the degree of this polynomial is 5. Here we have x plus 1, which is the equation of a line, but that's just like saying all these terms up here are 0, leaving just these two at the end. So even though this is a line, it also falls under the category of a polynomial, and the degree is equal to 1. We don't write that 1, but there is an x to the first power. And then for this one here, so there's 2 terms, both multiplied by numbers. Here we have x to the 100th power, then we have x to the 50th, and there's nothing else. But this is actually also a polynomial. And the degree of this one is equal to 100. So it turned out that these 4 were polynomials. It's going to turn out that these 4 are not. So starting with this one here, it kind of looks like a polynomial, but the problem is we have this -3 exponent. And in the definition, all the exponents are either positive integers or there's a number at the end. So just because of this, this is not a polynomial. So I'll just put no, not a polynomial. If you look at this next one, okay, we're adding things together. We have a 10, there's a 1 that's not written here, but the issue is 2 things. Here we have a square root, and nowhere in this definition is there a square root. And furthermore, this time we have this 1/4 exponent, and in this definition, all of the exponents are positive integers. So there's like 2 things that go wrong in this example, so nope. All right, in this one, the 5x to the 4th plus 4x minus 2, well, that is a polynomial, but this time the issue is the absolute value. Again, in our definition up here, there is no absolute value anywhere. So this one, again, this is not a polynomial. And in our last expression here in this equation, okay, here we have minus the square root of 2. I mean, that part's okay because we're just subtracting a number at the very end, but the issue is that we have this fraction with a variable in the denominator. So it's a fraction, but more specifically, there's a dividing by x, which does not occur up here. So here we have 4 examples of polynomials, and these 4 are not. So for this next part here, we're going to compare 2 graphs, x cubed and this x cubed with these other terms attached to it. So both of these are polynomials, but I have this fact written up here that says the degree of a polynomial determine what happens on the ends of the graph. Let's look at this first, y equals x cubed, a graph that we've looked at before. When I say the ends of the graph, I mean, I'm talking about like what's happening over here. Like on the right side, the graph is going up, and on the left side, the graph is going down. I mean, yeah, something different happens in the middle, but the ends are going in opposite directions. And I claim that this is determined by the fact that the degree is 3. And more specifically, an odd number. If you plug in positive x values and cube them, you get positive values back. But if you plug in negative x values, you get negative values back for y. This is why the graph goes up and then down on this side. So a degree 3 would have to have these 2 features. although the same would be true for x to the fifth, seventh, and so on. So I claim that if we put this graph in our calculators, on one side it's going to go up, on the other side it's going to go down. I think something different will happen in the middle of the graph, but that's what these terms do. This term here is going to tell us what the ends of the graph do, and then these three terms are going to just change what happens in the middle. I'm going to type this into my graphing calculator, and I'm going to sketch its graph, and let's see what we get. So I've typed it into my calculator. Here is the equation that I see. I'm going to try to get this on here as best as possible. The graph goes up, and then it eventually comes back down, and then it goes back up again like this. So if we look at the ends of the graph, well, this side is going down, and this side is going up. That's no surprise, and that's because of this x cubed. So an odd degree means the ends of the graph go in opposite directions, and then it's these extra terms that just mean the middle of the graph is going to be a little bit different. Let's try the same idea, but now comparing something that has an even degree, like 4. So the graph of x to the fourth, it looks a lot like the graph of x squared or x to the 6th, but the ends of the graph go up on both sides. And again, the reason is, if you take a positive number and raise it to the 4th power, it's a large value. But if you take a negative value and raise it to the 4th power, the negative goes away, making the numbers positive again. So I'm going to enter this graph into my calculator, and what I'm expecting to see is it's going to go up on both sides, but these extra terms are just going to determine something about the middle of the graph. You know, it might look a little bit different than this over here, but at least on both ends it is going up. So I just typed this into my calculator. It disappears a little bit off the screen, but I still think I can get a good idea of what the entire graph looks like. So I see that the graph comes down like this, goes down a little bit, and then it comes up here, then goes back down again like this, and this is where it like disappears off of the screen. But I know it's looping back up like this, and then it goes through this point. So, I mean, it's a decent sketch. It's, you know, not perfect, but I'm seeing something like that on my graphing calculator. And the main idea is that, well, on one end it's going up, and on the other end is going up as well, and that was determined by this. Now again, these other terms just meant that, well, when we travel from here to here, some different stuff is happening, but at least I know what's happening on the ends of the graph. One other thought, if there were maybe a 2 or a 5 next to this 4, it would just mean the graph increased faster. Or if there was a negative number in front of the x to the fourth, well, the graph would be flipped upside down. So we can use all those same ideas of transformations to understand the graph as well. So one final thought about the two polynomials that we looked at in this lesson. You may have noticed that when we graph these in the calculator, I could see the zeros pretty easily, and I'm going to mark them on here. Like, it looked like this was -2, 1, and 3. So that's easy enough to check in your table. I already did this, but -2, 1, and 3 are the numbers that made the equation equal 0. So that's why we call those things zeros. They're numbers that when you put them into the equation, they make the equation 0. Likewise, for x to the fourth, this function over here, it looked like -2, -1, 1, and 3 were zeros. Again, I checked those in my table, but -2, -1, 1, and 3 appeared to be zeros. We discussed in class that, well, if these things are zeros, it's very easy to write out a corresponding factor. So by that I mean, well, if x equals -2 is a 0, x plus 2 is a factor. The reason being, if you put -2 in place of x, it makes the factor 0. Likewise, x minus 1 is a factor because if you put 1 into place of x, it gives you 0 back. And x minus 3 is a factor as well. And the thing is, if you multiply these three factors together, it actually takes you back to this original equation. So said another way, if you graph this equation and you know the location of the three zeros, you know how to factor it without doing any difficult work. It's just a matter of copy down the zeros, write down the corresponding factors. The product of these things is equal to this, and you really easily just factored the equation. You can do the same thing over here. Again, we can list out all of the corresponding factors. It's going to be x plus 2, x plus 1, x minus 1, and x minus 3. If you multiply these four factors together, it would take you back to this original equation. So by using a graph, you can very easily factor your polynomial. I mean, you can also think about checking your answers too, like an x times an x times an x gives you an x to the power of 3, and a 2 times a negative 1 is negative 2, times negative 3 is positive 6. So just by multiplying a couple of the things in the equation, I'm just checking the first and last part of the equation, I believe that this is actually how it factors. Like over here, x times x times x times x, that's x to the fourth. 2 times 1 times negative 1 is negative 2, times negative 3 is also positive 6. So the point of this being, if you have a graph and you know the zeros, it's very easy to factor the equation.